recently made a video about 5 times in Earth's history in which plate tectonic events have caused major climate change events. And in this video, we are going to be talking about 5 more times that tectonic events have caused major climate change. First things first, I want to thank the sponsor of today's video, Brilliant. Brilliant offers amazing, fun, and engaging online learning tools and courses that I will talk about at the end of the video, so stick around to hear more about Brilliant and their amazing offer. So first things first, I want to recap a little bit if you didn't catch the previous video about the 5 times that plate tectonics have affected climate. I want to just recap what plate tectonics is briefly and how it affects climate. First things first, plate tectonics is the movement and interaction of Earth's lithospheric plates. Earth has a bunch of these plates made up of lithosphere, which includes both crust and the uppermost part of the mantle, and they bump into each other, and some subduct under others. Typically, oceanic crust subducts under continental crust because it's denser than continental crust, and they can also rift apart. They don't always push against each other. Sometimes they pull apart, and where plates pull apart from each other, they form rift zones, which often form ocean basins and lead to what's called mid-ocean ridges, where new crust material comes out. So crust material is getting subducted under into the mantle and recycled back into being mantle material and produced again at mid-ocean ridges, and it's this whole cycling of mostly oceanic crust. The continental crust doesn't really subduct, but this cycling is plate tectonics, and plate tectonics can greatly influence climate over geologic time. However, I do want to note, like I did in the previous video, that this is just one of many factors that affects climate, and other factors include things like atmospheric composition, solar radiation, changes in Earth's orbit and tilt, and other astronomical factors that change how much solar radiation Earth might receive, and therefore its temperature fluctuations. Biology, life itself, can affect climate greatly. I've talked about this, especially with regards to oxygenation events in Earth's history, like the GEO, the Great Oxidation Event, that occurred around 2.4 billion years ago after photosynthesis evolved and started producing oxygen, or I should say oxygenic photosynthesis evolved. There was photosynthesis that didn't produce oxygen. In any case, there's a lot of things that can affect climate that's not just tectonics, but tectonics is one of the major things. Also note, though, that tectonics typically influences climate on very long geologic timescales. This is not the case for all these factors that I just mentioned. For example, atmospheric composition, things like changes in greenhouse gas concentrations in the atmosphere or oceans can greatly affect climate and more quickly than plate tectonics. It's just because plate tectonics is so slow and occurs on geologic timescales rather than like human timescales that it causes much slower climate changes or delayed effects to climate, whereas atmospheric compositional changes can cause relatively fast acting effects. This is also why plate tectonics is never typically the sole cause for catastrophic events like mass extinction events in Earth's history, because slow change is not as harmful to life as rapid change. Typically, if things change slowly over time, geologic time, then life can evolve and adapt and be fine. But if things are changing really rapidly, say, for example, due to atmospheric compositional changes or a meteorite impact that changes atmospheric composition or blocks sunlight really quickly or causes major fires and heat waves, those changes are very rapid and life cannot evolve and adapt to those changes. So rapid change is more harmful, and thus plate tectonics can sometimes be, and has sometimes been, the trigger for other climate changes and stuff that then go on to cause mass extinction events. But it's typically associated with all these interconnected effects that then lead to a rapid spike or change in something, which then causes the mass extinction event. So in today's video specifically, the 5 tectonic events that I chose to discuss that have majorly affected climate in Earth's past ended up being largely involving opening and closing of ocean basins. 3 of the 5 events actually involve, or maybe 4 of the 5, we'll get into it, but they involve opening or closing ocean basins in some way. And this was just by coincidence, but it does speak to the fact that opening and closing of ocean basins really does heavily lead to changes in climate. For example, by changing oceanic circulation patterns, which, in turn affect atmospheric circulation patterns, and this can pretty significantly affect global climate. And I just wanted to briefly cover the fact that the opening and closing of ocean basins is typically summarized as the Wilson cycle in terms of plate tectonics. So what happens is you start with a stable craton, a stable, continental landmass, and then you might have rifting occur where a boundary forms because it's stretching apart, it's ripping itself apart. And this could be due to a lot of things. Typically, this kind of thing starts with plumes or hot spots in the mantle that kind of come up from the mantle and cause heating and pulling apart or thinning of the continental lithosphere, which then causes it to then start to rift apart. And this can typically start as like a point that then spreads out as, the plume comes up and causes that expansion. And that eventually leads to a full boundary of extension where the plates are pulling apart once they kind of form into two different plates. And you can see with the arrows here the movement of the plates apart from one another, causing this rift zone. And then eventually that can form an ocean basin because the lithosphere stretches out and thins out so much that, there's a basin there and water fills it, and then it keeps going and getting bigger and bigger and eventually can become an ocean. So that's the opening of the ocean, but then that ocean basin can also close, and closing of ocean basins typically, not typically, always occurs due to subduction. Subduction, again, is where oceanic plates will subduct under or kind of go beneath continental plates because they're more dense than continental plates. The reason that subduction is typically initiated is because there's some sort of plate boundary or boundary in which the forces are pushing an oceanic plate against a continental plate, and that will eventually force the oceanic plate under the continental plate. In this example, we can see that this started as what's called a passive margin, where the continental landmass passively gradually turned into the oceanic plate because of that rift zone that eventually formed the ocean basin. However, it turned into an active margin where the plates were then pushing against each other and the oceanic plate started to subduct under the continental plate because of some sort of forces. Probably, maybe this continental landmass hit another plate behind it and it caused it to stop or push against this oceanic plate because this oceanic plate was coming out of this mid-ocean ridge and pushing toward that direction. So that eventually led to convergence or a convergent boundaries where they push against each other, and that force toward each other led to the oceanic plate subducting under the continental plate, which then eventually closed the ocean basin. So that then led to, again, those continental land masses kind of merging into one, which then can be eroded down again into a stable craton. So you have this huge cycle that can repeat itself and has repeated itself with many ocean basins throughout Earth's history. And these events have caused major climate change events throughout Earth's history, and those are some of the examples I'll be giving in today's video. The first major sea or ocean basin we'll talk about that opened during the Mesozoic is the Tethys Sea. This sea formed between Gondwana and Laurentia as they rifted apart, breaking up Pangaea, the supercontinent that formed just before the Permian and contributed to the Great Dying, one of the largest extinction events of all time. I talk about how the formation of Pangaea and its breakup affected climate in my first How Tectonics Affects Climate video, and I'll link that to the top right if you're interested. But basically, the formation of this sea greatly affected ocean circulation and thus climate. When the rifting in the mid-Atlantic ridge began, in other words, when Pangaea started separating, started breaking apart, Laurentia, the continental landmass that included, like the North American craton, started rifting or moving northward, and Gondwana, which included South America, Africa, Antarctica, India, Australia, those landmasses all clumped together, and Gondwana started moving southward, breaking up Pangaea and forming the Mid-Atlantic Ridge, which started forming the Atlantic Ocean. But early on, this basin, when it started to form as a basin, was filled in by spillover from the Tethys Sea, which, because of Pangaea's really dry, arid climate, largely was evaporated when it spilled over into this relatively new and shallow basin. And this caused really extensive evaporite deposits, salt type deposits that form when water, evaporates, leaving behind its salts to precipitate. And that was mainly because, like I talked about in the previous video, Pangaea led to a really dry climate because it was such a big and, conglomerated continental landmass that much of the land, one, was kind of uplifted away from the sea and so far inland away from the sea that much of the land was really dry. And this really arid climate, especially of like central Pangaea, which was the part breaking apart, led to the evaporation of anything that spilled over into the early Atlantic basin. But eventually it did lead to the more stabilized sea and obviously eventually, over a lot of time, the Atlantic Ocean. However, the opening of the Tethys Sea wasn't the end of the story. The Tethys Sea also closed during the Mesozoic in the Cretaceous, which formed the Alps and nearby mountain ranges all along this convergent boundary where Africa was moving toward Eurasia at the time. And these newly built mountain ranges, obviously any mountain range that's, high, affects atmospheric circulation and thus can affect regional, but also, if large enough, can affect global climate. This wasn't the only thing that the closure of this sea allowed, though. It also allowed the exchange of plants and animals across this land bridge that had formed, which likely also altered regional climates. Like I talked about, life is a major thing that can affect climate. And so this land bridge allowing the exchange of animals and plants across this boundary really did affect the regional climates of either continental landmass. The closure of the sea also likely contributed to the warming trend during the Cretaceous. It did so by, one, reducing the capacity of the ocean to absorb heat, which thus increased surface temperatures, and two, lowering the solubility of CO2 in seawater due to changing ocean circulation and temperature. Again, however, this was by far the only thing contributing to the warming during the Cretaceous, especially by the end of the Cretaceous, where there was a big spike in rapid warming due to meteorite impact and the climate changes associated with that. But this is one of the potential contributing factors to this long-term warming trend in the Cretaceous. The second tectonic event we'll talk about in this video that had a major effect on climate is intimately related with the Tethys Sea and when it was spilling over into the newly forming Mid-Atlantic Basin, and that is the Atlantic Ocean. The Atlantic Ocean, like I had shown previously with that Mid-Atlantic Ridge, started forming during the breakup of Pangaea, and when the Atlantic became like a full-fledged ocean, it greatly affected ocean circulation, obviously. I mean, imagine if the Atlantic Ocean just poof wasn't there tomorrow. I mean, it's such a big part of modern ocean circulation, and this happened over a really long time, but now it is finally such, a huge ocean basin and still spreading, still getting larger, and so it is really integral to the ocean circulation system that is currently occurring on modern Earth and, controlling a lot of climatic factors on modern Earth. Whereas before it had split, ocean circulation was very different because it was always kind of limited to going kind of around Pangaea and, within the Tethys Sea area, but not getting in between the continental landmasses of Pangaea. Significantly, the rifting in the North Atlantic allowed warm equatorial waters to flow north, releasing heat to the atmosphere, and this contributed to the cooling trend during the Cenozoic. So right after the closure of the Tethys Sea contributed to the warming trend in the Cretaceous ended with the meteorite impact and the big warming spike and extinctions and all of that, and then it bounced back to a relatively, cooling trend throughout the Cenozoic, which was in part caused by by the formation of the Atlantic Ocean. Rifting in this region also caused volcanism and increased silicate weathering and carbon burial, thus decreasing CO2 levels. Like I talked about in the previous video, anytime you have increased silicate weathering rates, the weathering of silicate minerals like volcanic basalts or other igneous rocks, this contributes to carbon burial, or increases the rate of carbon burial by increasing the rate at which ions like calcium are transported to the ocean, which can form calcium carbonates, causing the storage of carbon long-term in the rock record. It also increases the flux and rate at which other ions like potassium, phosphorus, nitrogen are transported to the ocean, fueling as nutrients. They fuel primary productivity, or things like photosynthetic algal blooms, which increase the organic carbon burial rate and also cause the storage of carbon long-term in the rock record. So the storage or taking of the carbon from the atmosphere and ocean and storing it in the rock record thus decreases CO2 levels in the atmosphere and causes cooling trends. But don't get any ideas. This is a very long-term kind of effect that doesn't cause rapid change. So it's not like, well, it can help us offset the current increase in CO2 levels in the atmosphere, but not on a time scale that would compete with the current increase in CO2 levels. So it's not like it could really compete with that. It would long-term, but not in the short term. The Atlantic Ocean also, when it formed, provided new marine environments where more organic carbon burial could take place. So not only was there increasing weathering rates leading to more potential organic carbon burial favoring conditions, but also there was a new ocean available where that could take place, because that doesn't happen on land. You only get organic carbon burial, or carbon burial in general, in marine environments, or aquatic environments at least. I should mention that when Pangaea was forming, we did have the really coal swamp rich world of the Carboniferous, which led to a lot of organic carbon burial, and that was in terrestrial environments. But again, they were aquatic, and these swamps greatly dried up in the Permian because when Pangaea kind of took its full form, it really obviously, like I mentioned earlier, increased the aridity of the continental landmass and therefore greatly decreased the amount and distribution of coal swamps around, and that decreased the carbon burial rates in such environments. The cooling associated with the formation of the Atlantic Ocean also then triggered further cooling because it led to positive feedback mechanisms, which are climate mechanisms in which one climatic trend causes the exacerbation of that same trend. So cooling causing more cooling, or warming causing more warming. The reason cooling can cause more cooling is because once cooling takes effect and causes especially things like glaciation at the poles, or a pole at least, that leads to the increased albedo effect of Earth, which basically means like increased solar reflectivity, which means that more solar radiation is reflected rather than absorbed by Earth, therefore cooling Earth even more, which leads to more formation of ice, or spreading of glaciers, and therefore more reflecting of light, and therefore more cooling. That is the positive feedback that took place when glaciation finally started to form in the Cenozoic at the South Pole in Antarctica. The third major tectonic event that led to climate change that we'll talk about today is the formation of the Indian Ocean, which also took place or started in the Cretaceous. The opening of this ocean greatly altered, again, ocean circulation and heat transport within the ocean and thus atmosphere, and therefore also global climate. And I know what you're thinking. India actually hadn't hit Asia yet. It was headed up there, but it hadn't collided with Asia yet. So the Indian Ocean already started to form before India collided with Asia. Also, with these reconstructions of paleogeography at these different times in Earth's history, you might be noticing that the Tethys Ocean looks to be kind of where the Indian Ocean is today, or kind of took over where the Tethys Ocean was then. So what is the difference between the Tethys and Indian Oceans, and what marked the transition between the two? This is where you need to understand plate tectonics to really understand these pictures, because what you might see if we go back here is India is, kind of tied up in the big clump of continental land masses known as Gondwana down here during the Jurassic around 150 million years ago, but then around 94 million years ago in the Cretaceous, it started to break apart and move toward Asia, or Eurasia at the time, which eventually it collided into, which is where it is now. And here we can see it continued moving that direction right before it hit. But it is not as though India was just kind of floating on the water there to get to Eurasia. That is not how plate tectonics works. Actually, the Tethys Ocean basin was closing as India moved north due to subduction of the Tethys Ocean tectonic plate underneath, that's what those arrows mean, the subduction of that oceanic plate underneath the Eurasian plate. India was actually, rather than moving, or driving the movement, it was actually kind of just along for the ride of this subduction and movement of these plates toward Eurasia. So what did drive this movement? Well, it's important to note a couple things here about plate tectonics. One, subduction, once it's begun, the oceanic plate is subducting under the continental plate, and there's something called slab pull, where the subducting plate is kind of pulled under the continental plate at that point because it's getting into the mantle, and convection continues to kind of pull it or drive the subduction because it's just pulling on the slab, basically. That's kind of what we call it when it's subducting, is like a slab, subducting slab, and it's being pulled, basically, pulled under. The other thing that drove this movement was from the other direction. So in the front here, we have the subduction pulling this whole plate toward Eurasia, including India, and then we also had the pushing of India toward Eurasia because we had other ridges, other oceanic ridges where seafloor spreading was occurring. And that's kind of what this map is showing, is basically the age of the ocean's floor using radiometric dating, which show that the youngest material comes out from the spreading mid-ocean ridges, and we can see that new material was coming out of these ridges, pushing things in that direction in association with the slab pull. And what drives mid-ocean ridges and seafloor spreading is, again, mantle convection. So everything comes back to convection in the mantle and this, heat transport of the mantle and just mixing of the mantle, which, leads to all of this plate tectonic activity. So why did India stop when it reached Asia? Shouldn't the subduction have continued? Well, actually, continental crust does not subduct like oceanic crust does. It's just too buoyant. It's not dense enough, and it just, when it hits each other, it just instead smooshes together really hard and forms these really huge and high mountain ranges. And that's why the Himalayas is, the highest mountain ranges, or has some of the highest mountains, is because it's continent on continent convergence. Anytime you have mountains that form due to ocean subduction underneath a continental crust, you'll get mountains, but they won't be quite as high as you get when you get continent on continent convergence. And this, like I mentioned, leads us to the Himalayas, which is actually our fourth major tectonic event that led to climate change. So the previous one was about the closure of the Tethys Ocean. So remember, the Tethys Ocean plate, the oceanic crust that the Tethys Ocean was over, covering, or the water of the Tethys Ocean was covering, that crust got completely subducted and completely closed when India hit Asia. And then behind the Indian continental landmass came the Indian Ocean, which was a whole different set of crust. So the difference between the Tethys Ocean and the Indian Ocean, to answer our previous question, is the crust underneath it is completely different. It's new because it spread from that mid-ocean ridge behind it, whereas the Tethys Ocean crust that was there has been fully subducted under the Eurasian plate. There are some remnants of the Tethys Ocean or seaway still around, like the Mediterranean Sea and other seas in that region, but the big ocean basin was closed. Then we had, again, the collision that led to the Himalayas, which completely changed the climate of India. As we saw, India was kind of this floating landmass which had these seas covering where now the Himalayas are. Can you imagine that? It had shallow seas and this, carbonate production environment where it was kind of like this destination beachy environment. And now it's this thing covered in these huge mountains. It's just such a huge shift in climate due to plate tectonics. This collision also led to the formation of the Tibetan Plateau, which altered atmospheric circulation greatly because it's so tall. And this led to the Asian monsoon system, which significantly impacts regional climate in that area. Lastly, the fifth tectonic event or events that eventually led to or kind of triggered the shift into our modern ice age that we're in today is one, the formation of this kind of seaway passage between South America and Antarctica occurred around 34 million years ago, and this led to a major shift in ocean circulation that kind of triggered the modern glaciation period, because before opening, warm waters from the Pacific circulated around Antarctica, which obviously kept it somewhat warm, preventing major glaciation, whereas after the Drake Passage formed, it allowed the Antarctic circumpolar current to become, isolated around Antarctica, basically isolating that climate to kick off the Ice Age and the major glaciation period that, started around this time. The second major trigger of the modern Ice Age, more recently around 3 million years ago, was the formation of the Isthmus of Panama, which led to the Great American Biotic Exchange of flora and fauna, plants and animals between these two continents, which was major for biodiversification, and we know that life can significantly influence regional climate and global climate, as I talked about previously. But this wasn't the only thing that this land bridge caused. It also led to a major shift in ocean circulation in the Atlantic and Pacific Oceans, which impacted global climate and contributed to the further triggering of the modern ice age. So the kind of thing that kicked off the general cooling trend from 30-ish to 3 million years ago was the Drake Passage, which then the formation of this land bridge kind of dropped us into the modern ice age from 3 million years ago to present, which I talk about in my What Kicked Off the Modern Ice Age video, which I'll link up here if you want to go check it out. With our knowledge of how these tectonic events kicked off the modern ice age and how they might affect climate in the future, we can run models, do data analysis, probability statistical analysis to predict what might happen in the future based on current tectonic movements. And if this is something you're interested in, I highly recommend building your skills in data analysis, probability, and statistics using Brilliant. Brilliant offers thousands of courses that don't even feel like courses, first of all. They're just so fun and engaging and time effective, and they really do help to increase not only your skills in like mathematical or computer sciences, but also other scientific fields, including astronomy, geological concepts, and other things that I talk about on my channel that I know you guys love learning about. So I highly recommend that you go check out Brilliant right now at my unique link in my pinned comment below, brilliant.org/geogirl, which will give you 1 full month free of Brilliant and 20% off an annual plan. Again, guys, I cannot recommend this enough. It is so fun. I was just doing a course on terraforming Mars and like the things we'd have to think about Earth and how it's different and similar to Mars and Mars's features that make it terraformable or not, or all these things that really kind of help you see the connections that we have to make in our, day-to-day world with concepts like this. I mean, it's incredible that Brilliant relates things so much to just our daily lives, which really helps understand the concepts like better than I could do, I swear. So yeah, go check out Brilliant, brilliant.org/geogirl for that special offer. I think you guys will really enjoy it. If you've already gone and done your Brilliant lesson and you want to stick with me for a bit, I recommend checking out the first plate tectonics and associated climate change video that I did, which I'll link up here if you haven't seen it. And with that, guys, as always, my references are linked down below, and I can't wait to see you guys next time. Bye.